Hello and welcome back to Unit 12. In this part of Unit 12, we're going to focus on rotational kinetic energy. You may wonder why throughout this class we have focused on blocks sliding down a ramp instead of thinking about balls rolling down a ramp. And the reason is because the ball, in addition to having translational kinetic energy, also has rotational kinetic energy. Translational kinetic energy is the 1/2 mv squared that we have encountered throughout the semester, the last few units since we learned about energy. Rotational kinetic energy is going to be 1/2 times the moment of inertia times the angular velocity squared. It takes some energy to get an object to rotate. Therefore, there is energy contained in that rotation. Now, for an object that is rotating without slipping, we can use the fact that V equals R omega to plug in that the angular velocity is the velocity of the center of mass divided by the radius squared, in order to be able to simplify the work that we're doing. Let's consider an example. In this example, we have two identical balls rolling down two different inclines. The inclines have the same height, but different slopes, as shown in the pretty picture. So here are my two identical balls sitting at the top of the two inclines. At the top, both balls have gravitational potential energy, and if we assume that they're not moving at the top, only gravitational potential energy. At the bottom, they have both rotational kinetic energy plus translational kinetic energy. So that'll be 1/2 I omega squared plus 1/2 mv squared. For the bottom, we're assuming that gravitational potential energy is 0. I should have said that a moment ago. Plugging in that omega is V over R. I can now combine these two terms. I have a 1/2 in both of them. I have a V squared in both of them. In the first term, I have an I over R squared, and the second term is just 1. If I now use conservation of energy to equate these two, I get that, not times 1, times the mass, I'm sorry. I get that mgh equals 1/2 v squared, the moment of inertia, divided by r squared plus m, in parentheses multiplying the v squared. We can plug in that the moment of inertia is 2/5 mr squared for a solid sphere and get a formula for the velocity. But from what we have here, we can see that nothing in our analysis depends on the incline. And so the velocity will be the same for both. However, because the inclines are different, they will have a different angular or different acceleration. The one on the steeper incline will have a larger acceleration, and therefore the one on the steeper incline will reach the bottom first. Now let's consider a variation on this idea. And instead of having identical objects moving down an incline, we're going to vary the objects. We're going to use a cylinder and a hoop. For both of them, I can do the same analysis that I did on the previous slide, that the energy at the top has to equal the energy at the bottom. The energy at the top will be gravitational potential. Energy at the bottom will be translational kinetic energy plus rotational kinetic energy. And just as I did before, I can plug in and factor out that omega is V over R. At this point for this analysis, before I can proceed onward, I need to know what the moments of inertia are. For a solid cylinder, looking at the table that was provided, the moment of inertia is 1/2 the mass times the radius of the cylinder squared. And to be consistent with the notation, I use little r over here, so I'm going to use a little r over here as well. For a hoop, it is mr squared. Plugging in the moments of inertia for the cylinder, I get mgh equals 1/2 v squared plus, not plus, times the mass plus 1/2 mr squared divided by r squared. This works out that v squared equals 4/3 gh. For the hoop, I get mgh equals 1/2 v squared times the mass plus mr squared divided by r squared. R squareds again cancel, and I can solve for v squared equals gh. You can see that because the moments of inertia were different, the velocities are going to be different when they hit the bottom of the incline. With the cylinder going to have the larger velocity. Therefore, the cylinder wins the race. It reaches the bottom first, and it is moving quicker. The last two examples have worked with conservation of energy. But as you can imagine, you can take energy out of rotation, or you can add it in. Therefore, you can do work on rotations. Translational work was F dotted with delta R, the force dotted with the displacement, or in magnitude was F times delta R times the cosine of the angle between them. We can now write the magnitude, or it's a scalar, so there's no magnitude. We can write the value for translational work that it's going to be the torque multiplied by the change in angular position that happens. So when cosine of theta is 1, meaning that the force acts in the same direction as the displacement linearly, we get F delta R. The two formulas are very analogous in that case. There is an example using rotational work in the next part of this unit.